Okay, so this is going to be a linear algebra interlude. Okay, so we're not going to do anything in here at the moment with anything more than 2 by 2 matrices and vectors in R2, because that's enough to exhibit why I'm going to teach this to you guys now. So properly, you'll do this in full detail in either Math 206 or Math 244, depending on which way your track through the math classes takes. If you're on the whole ride for the honor sequence, then we'll be doing 244 next quarter, and we'll see this in a full treatment. But I think almost everyone in here has seen matrix multiplication before, but probably not with an explanation of what it was that it meant. When you saw matrices before, you may have seen them in the context of solving systems of equations and row reduction. So maybe an earlier context for matrices is you may have seen this in the context of Gaussian elimination. So systems of simultaneous equations. You maybe were shown how to multiply matrices. I'm going to remind you how that goes. But almost certainly without any sort of geometric explanation for why. I will point out that if you are interested in linear algebra, which is probably the language that most strongly unifies all the different areas of math and science right now, there's a really nice sequence of videos. You can sit around and watch nerd videos on YouTube, but 3 Blue, 1 Brown has a sequence of videos called The Essence of Linear Algebra. Essence of linear algebra that really sort of describes what's going on generally with ideas from linear algebra, and of course all of his videos, really beautiful visualizations of it all. So we're going to do kind of a cut down version of the sort of ideas that show up in this sequence today. So first thing is, what is a matrix? So a matrix is just an array, or in some textbooks they just say something like a square of numbers. Now they don't have to be square. I've seen this in a book before, which is why I write this. More properly, you'd write a rectangle of numbers. So for example, I could have a matrix A. Usually we use capital letters to designate matrices. It does not matter. And if I want to write the entries down in a way that records where they sit in the matrix, I can use this subscript notation to say, hey, that entry right there is in the first row and first column. This is the first row, second column, second row, first column, second row, second column. Okay. More usually in classes at this level, we might just write A, B, C, D. Okay, now matrices are basically vectors. They're just numbers once they're in a spot, they can't move out of that spot. So just like you can add vectors of the same size, you can add matrices of the same size. You can also multiply a matrix by a scalar in the same way that you could multiply a vector by a scalar. So if you took a scalar C and multiplied it by the matrix, choose a different letter here, a scalar K and multiplied it by the matrix A, B, C, D, you'll get, just like with vectors, KA, KB, KC, KB. All right, so I'm trying to convince you right now that matrices act a lot like vectors, and since vectors act a lot like numbers, we could think of these things as a collection of objects we can do math with. Right? I can also add them. A, B, C, D, as long as they're the same size, E, F, G, H, just like with vectors, we just add entry-wise. A plus E, because those are in the 1, 1 spot, E plus F, because those are both in the 1, 2, C plus G, and D plus H. Okay, so again, they're acting like numbers. Where they're different than numbers is that for matrices of appropriate sizes, we can actually define a multiplication. So vectors, I should say, unlike vectors, where vectors we had this weird problem where we had multiple products we could set up on vectors, but one of them produced a scalar and the other one didn't. I mean, you got a vector out the other side, but it didn't seem like it naturally produced a vector that combined the two that you started with. The cross product gave you that orthogonal vector, right? So matrices have a multiplication on them that acts more like numerical multiplication. So I'm going to define this in terms of the dot product. So if I have a matrix A, B, C, D, and I multiply it by a matrix E, F, G, H, since we're only dealing with 2x2s right now, I'm going to do this sort of special case where this is guaranteed to work. These are appropriate size. You'll learn this in linear algebra class if you haven't seen this before. These are both 2x2 matrices. And the rule that they teach you if you've learned this before is, oh, if those two numbers match, then you can multiply matrices. How many of you actually seen this before? Like 3 or 4 of you have seen this. So the way we define multiplication of matrices is going to seem kind of artificial, but we think of the rows of this matrix and the columns of this one, and we take dot products. So if I think about this matrix instead as row 1 and row 2, and I think about this matrix as column 1 and column 2, so I've got the rows of this matrix and the columns of this one. The way that I produce the output is I just take dot products of these things. The matrix multiplication is defined to be row 1 dotted with column 1, row 1 dotted with column 2, row 2 dotted with column 1, row 2 dotted with column 2. And notice, as long as the rows and the columns are the same size, I could have 1 column here, 2 columns, 3 columns, or 4 columns, and this will still be a well-defined operation. So if I'm going to write down a specific example, suppose I told you that I'm interested in 1, 2, 3, 4 times 5, 1, 10, 6. Multiplication of matrix. In fact, let's even go easier than that. Let's just do a column first. Yeah, we'll start here. So the way I'm going to produce the answer is I'm going to take row 1 and I'm going to dot it with column 1, and that's the 1, 1 entry of the result. So the dot product of those two vectors is 1 times 5 plus 2 times 10. This row dotted with this column, so I multiply and then add. For the next entry, I'm going to take the same row and I'm going to dot it with this column. 1 times 1 is 1, 2 times 6 is 12. For the next entry, we take row 2 and go by column 1, which gets us 15 plus 40. And then finally, row 2 times column 2 gets us 3 plus 24. And so the result of that multiplication is 25, 13, 55, 27. Now in the same way that I did this for a single, for a 2 by 2 and a 2 by 2, anytime I have this dot product set up, I can produce a multiplication. So here's a common one. I could take something like 1, 2, 3, 4, and I could multiply it by a column vector, say xy. The same procedure still works here because this dot product is defined, right? I can take the dot product of row 1 with column 1. Actually, what should the shape of the output matrix be here? How many rows should it have? 2. The number of rows that we had here. How many columns should it have? 1. The number of columns we had here, right? So this is going to have 2 rows. So we're going to do the vector 1, 2 dotted with the vector x, y. And then for the second entry, we'll have 3, 4 dotted with the vector x, y, which will give us x plus 2y in the first entry and 3x plus 4y in the second. That's the right shape. All right, now, even for those of you that have seen this before, the first time that you see this done, it just looks like a pile of arithmetic nonsense. Like, I just wrote a bunch of squares on the board and defined these operations and told you, oh, they're really important, but I didn't tell you what they represent. It's not even clear why this is a useful thing to do. So, to remind you of a task that you really, really, really hated if you've done this before, and I know that you guys all have done, one place where matrices show up is in Gaussian elimination. But of course, they teach you the method of elimination without teaching you matrices, which means they're telling you the method without the way you actually should be doing it. So if I give you a system of simultaneous equations like x plus y is equal to 3 and 2x plus 1 is equal to negative 1, you probably learned a method where you pick a, oops, I should probably put a y there. Pick a method where you multiply this equation by -1 and then add, which eliminates one of the variables, and then you back substitute once you've got the y for the x. Like, this is like an Algebra 2 idea. They are fun? Then you're going to love linear algebra because that's a lot of that going on in linear algebra. So what they were really doing there, even if they didn't show you, is this is actually a matrix problem. 1, 1, 2, 1 times xy is equal to 3, negative 1. So this problem that you've seen in lots of classes before actually is encoded in this matrix problem. You can see it because 1x plus 1y, that's x plus y. So 1x plus 1y is equal to 3. The first line of this output is that equation. And 2x plus 1y, the dot product of this row with this column, gives you this side of the equation. So what that does is it lets you sort the variables out into a vector and all the coefficients into a matrix. So this sort of encoding of a problem into a matrix problem, I mean, this doesn't look like something that you can solve with algebra. There's no dividing, you do manipulations here. This, if you wrote it down symbolically, would look like this. Oh, a matrix A times a vector x is equal to a vector b. A times a variable matrix, a variable vector, is equal to some known vector. That looks like the sort of equation they teach you in like baby's first algebra 1. If those were numbers, what would you want to do here? Divide by A, right? That's like the thing that you want to cry. If I put plot it. Okay. Yeah, so it's a plot it, figure out the x. All right. Cry is a usual comment I get in some classes. So I'm sorry for missing. Turns out a lot of people that math makes a lot of people tearful. Probably enjoy. Okay, so what you really want to do if you see an algebraic equation like ax is equal to b would be, man, it would be awesome if I have ax is equal to b, then you learn that x is equal to b over a. Of course, there's no such thing as division. I pointed this out last term. Division doesn't exist. There's just multiplying by inverses. So what you really did when you did this, what you really did was you multiplied both sides of the equation by the inverse of a, and that told you that a is equal to a inverse b. Now for numbers, the inverse and the reciprocal are the same thing. So x is equal to b over a. And here's why there's an entire class in this stuff. If you take your sort of matrix setup and you try to divide by a, not every matrix has an inverse. Every number has something I can multiply by that cancels it. Not every matrix has that. If you remember for your Gaussian elimination problems, sometimes there were no solutions and the system was inconsistent, and sometimes there were infinite solutions. So that shows up, that actually is recorded in the matrix. So I can't divide by A. And sometimes A inverse might not exist. Well, if it doesn't exist, then I can't eliminate it. This leads to inconsistent or infinite solutions, depending on the particular problem. Okay, now the last part of the overview here before we get into what a matrix is actually doing is, you guys remember that when we did the cross product, it was defined in terms of a thing called the determinant. So, and then we spent all that time talking about the algorithm for computing the determinant. You got a bunch of you know the one where you like do the 3 diagonals and then the other 3 diagonals and multiply and add or whatever. So what the determinant actually is, is it tells you if this exists or not. That's what the determinant is. The determinant is a method for deciding, is there an object I can use to cancel this out or not? So it's not just a numerical algorithm. The determinant of a matrix, if it's equal to 0, there's no inverse. If it's not equal to 0, there is an inverse. So we did the entire first half of Math 206 in 15 minutes. Anyway, this is an opportunity for me to sort of bring ideas together that you've seen before and tell you all of it was linear algebra. But because you haven't taken the class, we can't actually tell you that. All right. So now let's look at a concrete example of what a matrix represents. So I'm going to write a matrix down. So I'm going to write down the matrix 1, 1, 0, 1. So what is a matrix? How do people think about what matrices actually do? And this is relevant to our study of derivatives. So the thing I'm going to do right now is going to link up the idea of matrices to the study of derivatives. So let's take a look at what would happen if I took that matrix. I'm going to take that matrix and I'm going to make it into a function. I'm going to make a function f of a vector x is equal to ax, which really means I'm going to take the matrix 1, 1, 0, 1, and I'm going to multiply it by xy. It eats a vector, and whatever that vector is, it gets multiplied by that matrix. Seem reasonable? If you like, you can think of this as f of x and y. So there's some really easy vectors that we could plug in to that matrix. So for example, we could put in the vector 1, 0. So if I feed the vector 1, 0 into that matrix, or into that function, so f of the vector 1, 0 is equal to 1, 1, 0, 1 times 1, 0, which is, you get 1, 0 out the other side by doing that? Let's see. 1 times 1 is 1. 1 times 0 is 0. And on the bottom we get 0 times 1, which is 0, and 1 times 0, which is 0. So the same vector went in as came out. I'm using that to be the image of the yellow vector. Orange. Okay, how about this one? There's the vector 0, 1. What happens to it? F of 0, 1 is equal to 1, 1, 0, 1 times 0, 1. And that gets me the vector 1 times 0. Oh, God, if I made a vector, if I make it so it doesn't do anything. No, I'm good. 1 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. 1 times 1 is 1. So I get out the vector 1, 1. Want to do that multiplication? Okay, so if I plot that, I should put this in yellow here to be consistent. Here's my input vector 0, 1. And what came out this time was the vector 1, 1. So one way of thinking about what this function has done is it's taken our original input space. So like, actually, maybe I'll draw this in 2 pictures so you can be more clear what's going on here. So I'll put a picture here and a picture here. And my input vectors were 1, 0, and 0, 1. And the output vectors were 1, 0, and 1, 1. So now my question is, what would this linear transformation, what would this function, this linear function, have done to a square? If I had started here with a square, well, let's see. Maybe we should figure out what's going to happen. If I'm going to figure that out, I should probably figure out what happened to that point also, right? So if you took the vector 1, 1 as an input for this function, and you did the same exact thing here, right? So now I'm going to I transformed 1, 0 into 1, 0. I transformed 0, 1 into 1, 1. Let's see what happens to the vector 1, 1, because that'll tell us where the other corner of the square went. 1, 1, 0, 1 times 1, 1 is, I heard somebody say it. 1 times 1 plus 1 times 1 is 2. 0 times 1 plus 1 times 1 is 1. 2, 1. So it took this. It took the square and it distorted it into a parallelogram. So what matrices actually tell you is a way of transforming R2. They transform the plane. Like 2 by 2 matrices are things that tell you, hey, the entire plane is going to be affected by this transformation. Any shape that you draw basically is going to be tipped over that much in the x direction. So you can imagine the coordinate system over here is a bunch of little squares. When you do this matrix to it, what you've done is you've taken all those little squares and you've turned them into little parallelograms instead. So if you kept this going where you had a square and a square and a square and a square, and you fed all of those squares into this same multiplication, what you would find is that you get this. So matrix multiplication is a change of variables. It changes the domain of a function. It changes this coordinate system into this coordinate system. Oh, it's such crappy chalk, it survived the fall. All right, so what I want you to take away from this is a matrix anything determined by a matrix multiplication changes the shape of the space that it's been applied to. Every vector over here can be written as a combination of 1, 0, and 0, 1. So every vector over here can be written as a copy of the distorted versions of 1, 0, and 0, 1. And that distortion is consistent. That distortion is told to you by this matrix. Okay, so that's enough of the crash course in linear algebra. The reason to teach this to you is because this is a much more natural way of talking about what derivatives are. Okay. I'll write these up in some notes that I have not posted yet. I have a bunch of notes, I just have to write them, so they're handwritten right now. Okay, so let's change gears for a second. Yesterday, I told you about a black box theorem. I told you guys, hey, I wanted you to write down something like, what was the theorem I gave you? It was something like if H is equal to F, G of H
equals F X H.
F of X of H,
Y of H.
Y of H.
Then G prime of H equals the derivative of F with respect to X times the derivative of X with respect to H.
Okay, so Fx times xh
Plus the derivative of F with respect to Y times the derivative of X or Y with respect to H.
Okay. Okay, I think maybe the way I wrote it down yesterday was df dx dx dh plus df dy dydh. And I asked you to just accept that rule for now. So the most natural way of thinking about this, so if I was going to write this over here, this properly, I would have written G composed with H. G composed with F. Is that what I want? F composed with a function xy. That's what we really did there, right? We have this function xy, which is a vector function, and then whatever that vector function is, we fed it into F. Does that make sense? That says whatever the x and the y are, take those values, evaluate them, and then stick them into the formula for F. So F is a two-variable function here. So we're taking x of h and y of h and plugging x into the r spot and y into the s spot. So another way of looking at this rule, if I know some matrix multiplication, I might look at that and say, what's actually happening here is that the derivative of g with respect to h sure looks an awful lot like the matrix df dx df dy times the matrix x with respect to h, y with respect to h. Once you know some linear algebra, you start seeing these relations. It's also a dot product, right? This is a dot product of two vectors. It's a dot product of df dx, df dy with dx dh, dy dh. The other way of looking at this is df dx, df dy dotted with dx dh, dy dh. Make sense? So that at least getting from this formula that I told you to believe, right? If you have that formula in front of you, you could either think about it as a dot product of vectors, or you can think about it as a multiplication of matrices. After all, if I have this matrix and I try to calculate the output, it's the first row dotted with the first column, and then you're done because that's it. There's one row and one column. So this thing right here, and this is where Stewart completely falls apart, I think. This thing in higher level math and in engineering and science context, this is called the derivative of f. So the derivative of f, which is also in some context called the Jacobian matrix, is the matrix that stores the partial derivatives of f inside of it. And this would be the derivative of the vector function x. This is where, if we're assuming here that x is equal to x of h, y of h. So essentially what this is saying is, oh, well, if I'm using this capital D to stand for derivative, what this rule is saying is maybe I could call this the derivative of g. And then we get something out that looks an awful lot like the chain rule that you already know. If we're willing to use matrices to talk about like a setup like this, the chain rule that you guys know from calculus, what did you learn the chain rule? Calculus 1 says something like d, the derivative of f. If you have f of u of x, that d by dx of f of u of x is equal to f prime of u times u prime of x. Or in short form, f d by dx.
Wait, isn't the UX supposed to stay in the F prime of X?
What's that?
Is U not still?
Oh, yeah, I'm just emphasizing the fact that, yeah, we can put u of x here.
Oh, okay.
Because I was just going to write this version down, which is the other. This is the short form. If you go to the back of the textbook and you look up the chain rule, that's what it says. Right? The chain rule says if f is composed with a function u, you take d by dx of f of u is equal to f prime of u times u prime. So that is the chain rule. So one variable chain rule. Now, why did I not ask you to read 14.5 before we came in here today? Because if you're trying to guess what the chain rule looks like in more variables, you can either go through kind of a long-winded explanation of why these long expanded formulas hold, or I can teach you just a tiny little bit of matrices. If you're willing to believe that I could write down a matrix for the derivatives of f, and a matrix for the derivatives of the function x, and that just from the thing I asked you to black box, you get a relation that looks like, well, this thing that I wrote right here looks an awful lot like what I just said was the derivative of f composed with x is equal to the derivative of f times the derivative of x. That is the chain rule from one variable calculus. The derivative of a composition is the derivative of the outside function times the derivative of the inside function. Okay, so we're going to be doing some, this is basically, I'm setting the stage for like more complicated ideas that you're going to see in your classes later. I know I'm going out of sequence with the entire math sequence, but you actually would have been better served if you learned linear algebra before you took this class. But we can't teach it that way. Yeah.
So F and X, how you put them on there, those are just the compressed versions. So like no matter how many variables you have, you just keep adding on the, okay.
Yeah, so like if I had, so let's say, let me give you an idea of like what that would look like in practice. I'll do an example. I recognize that I am just telling you it works this way, and then we're going to go through and do some actual computations here. But let's take a look and see. Let's write down something like, let's assume as before that we still have the rule that if I have the derivative of a composition, so d by dt of f composed with x was equal to df dx dx dt plus df dy dy dt. That's that black box chain rule that I asked you guys to deal with here. So this is for a scalar valued function f. Well, let's actually see. If I gave you something like f of xy is equal to x squared y, and then the function capital X, or sorry, vector x of r and s is equal to r squared r plus s. There's an f and there's an x. Now there's a couple different paths we can take if we want to calculate the derivative of this function. Suppose what I tell you is I would like to know the derivative of, actually do I need, no, sorry, wrong way. This all has to be a function of the same variable. I'm getting ahead of myself. X of t is equal to t squared t plus 2t squared. Now I've got the setup correct, because x and y both have to be functions of a single variable t, right? That's what we're asking here. And f is a function of two variables. It eats those. So the way the book wants you to do this is to think about it this way. It says, well, you could just do this composition. F composed with x is like f of this function. So when f looks for the variable x, it goes over here and says, look, x is equal to t squared. This is going to be the function x of t, and this is going to be the function y of t. So if you put that function into this one, you end up with it's f of t squared t plus 2t squared, because that's what x and y are. And then if you feed those into the formula, you get t squared times t plus 2t squared. X squared y. There's x, there's y. This is x squared y. So you could just keep multiplying this out. So t to the fourth times t plus 2t squared, which is t to the fifth plus 2t to the sixth. And so if you wanted to calculate the derivative of this, so d by dt of f composed with x is d by dt of t to the fifth plus 2t to the sixth, which is 5t to the fourth plus 12t to the fifth. Easy, except it's kind of grinding to do this. And you can imagine, in general, this approach is going to be gnarly because the functions aren't going to be simple combinations of x and y like this. And there could be millions of variables. I don't want to have to produce the composition to calculate the derivative is the point. Right? I prefer not to do that. So now let's use this formula instead. We'll do an example calculation. So what the formula says is, another way of doing d by dt of f composed with x would be df dx, dx dt, plus df dy, dy dt. Well, that's pretty easy. df dx is 2xy, and dx dt is 2t, and df dy is x squared, and what is 1 plus 14, right? Oh man, but now I got x's and y's all mixed together with t's. What am I going to do? If only I knew what x and y were equal to. Oh, look, there they are right there, x and y. So if I wanted to keep going, I could actually just do the substitution at this step after I've computed this derivative, right? In practice, though, oftentimes what happens is you get asked a question like, calculate the derivative of f composed with x evaluated at the point where t is equal to 1. And here, you don't even need to substitute in because you know everything that's supposed to be present in this. If t is equal to 1, what's x of t? T squared, which is 1. What's y of 1? Let's see, 1 plus 2. So 1 plus 2 times 1 squared is 3. So x is 1, y is 3, t is 1, which means d by dt of f composed with x at t is equal to 1 is 2 times 1 times 3 times 2 times 1 plus a 1 squared and a 1 plus a 4 times a 1. We did no substitution. We numerically evaluated things. We didn't have to do some sort of variable expansion to do this. We could just calculate it directly from here. I think that's safe to say, if I've done this right, what, 6, so I got 12 plus 5, is it 17? Okay, let's go back over here. I do all this work instead, and I put in t equals 1. Oh, look, they match. So at least I've done some math correctly this morning, right? If I put in t equals 1 here, I also get 17. So these match with each other. This is basically what we did right here. This is chapter 14.5. Chapter 14.5 is you've got a bunch of functions. They've got other functions inside them. You calculate derivatives using a formula like this, and you plug in numbers. That's like the whole chapter. It's how you deal with the chain rule in cases where you've got compositions of things that are not scalar valued functions. What I wanted to show you, and the point of this example is, I want to show you what this would look like if we did it with the matrix version instead. This is not part of 14.5, but it cleans up some of this calculation. Okay, so if I was going to do it that way, That would be like saying the derivative of f composed with g is equal to x is the derivative of f times the derivative of x, which is fx fy times xt yt. That's what the matrix version of this rule would say. And that just gets you the same thing we wrote up here. 2xy, what was the other one? What's the derivative of that? Oh, x squared. This is the derivative of f with respect to x, the derivative of f with respect to y, and then we would multiply that by a column vector, which is x with respect to t, which was 2t, and y with respect to t, which was 1 plus 4t. So in practice, this is the way people write this down in a lot of contexts, because what you're doing is you're separating the derivatives into pieces where you can see what each piece of the function is doing. This is the derivative of the function x of t, and this is the derivative of the function f. You can think about this as sort of being like the change of variables part of it, and this is being the derivative of the actual function. So take the derivative of the function and then transform it into something else. So not necessary, but kind of clean and a really good way of thinking about what derivatives are. Derivatives are linear functions. You already know that. A derivative is a linear function. Derivatives give you tangent lines, right? So derivatives are intrinsically about creating tangent lines or tangent planes. Matrices are linear functions. So a derivative being represented by a matrix should not be surprising once you start to get your hand around, once you get a handle on what matrices actually are. And so we'll see a lot more of this. We'll see more of this if we go on 244. Those of you that are going into fields where this kind of approximation is really important are going to see tons of this way of thinking about stuff. Okay, so let's do one more example here. And here's where I'm going to give you a preview of the book's method for doing this. So how would the book tell you to do this? So the book tells you, hey, it's the book method. And then maybe you can see my irritation with what the book tells you to do. The book says, hey, if you happen to have a function f of x and y, and x was a function of t, and y is a function of t, then you do this little chart where f is on top, and then you say, oh, there's these things called intermediate variables. And then x is a function of t, and y is a function of t, and these are called the final or independent variables. And then the way that you do the chain rule is, if you want to calculate df dt, you follow the branches of the tree from f down to every t that appears, multiplying by partial derivatives along the way. This branch is df dx, this branch is dx dt, this branch is df dy, this branch is dy dt. So if I want the derivative of f, I have to crawl from f down to every t. So this will be df dx, dx dt, because that's one of the paths from f to t. And then there's another path that goes df dy, dy dt. To me, that's an algorithm with absolutely no grounding in what's actually happening, right? There's not any idea that composition of functions is happening here. It just gives you a way of computing what the chain rule has to be, but without telling you what the chain rule is actually doing. Oh, what if there's more variables? Right? So if there's more variables, maybe you have f is a function of x, y, and z, and also x is a function of r and s, and y is a function, of r and s, and z is also a function of r and s. Then you build your tree. F depends on x, y, and z. X depends on r and s. Y depends on r and s. Z depends on r and s. So then you get this, what we'll do now is we're going to do df. Let's do the partial of f with respect to s. F is a function of ultimately f will be a function of variables r and s, because those are the independent variables. And so what the formula tells you to do is start at F and go down every path until you get to S. There's one path that goes to S. There's a second path that goes to S. There's a third path that goes to S. So df ds must be df dx, dx, ds, df dy, dy ds, df dz, dz ds. It gives you an algorithm, but that's telling you what it actually is that you're doing. So this we will talk about. So this is actually the real content of 14.5. So now read that. This is the approach that you'll see. And I will tell you, I'm going to pitch really hard for this. A better way of thinking about this, even though this is math you haven't seen before, would be to think it's literally just F composed with G is equal to df dg. This is the proper way of doing it, and I wish you guys had more linear algebra. All right, I'll see you maybe at 12:30, definitely tomorrow for the lab day.